In this lecture, we shall be primarily discussing about the compression members. So when we are talking about the compression members in structural steel buildings, so there may be different kinds of structural steel members. Let us say we have this industrial structural steel platform, and on this platform, this is the beam, and this is the what we can say either it is a steel column, or we can say it is a compression member. Second option, let us say we have this what we can say a structural steel column again. This is let us say cantilever beam, and that is being supported with the help of this particular bracket. So that is also known as either a strut, or we can say the primarily resisting force for this particular member, that shall again be compression. Third option, let us say in a structural steel building we have this kind of bracing, and in this particular building, let us say we are having this particular horizontal force along this direction. So in this case, this member shall be primarily be taking the compression, and this member that shall be primarily be taking the tension. So this again, that is also a kind of we can say compression members. So that was the basic introduction to what we can say different kinds of compression members in structural steel. Now, it is not that only the columns are compression member. Different kind of members in structural steel can be compression members. Now, first thing first that we do need to understand that when we're talking about the compression members, the main function of the compression member obviously that is to take the compression force, and the capacity to take the compression force that is primarily depending on the height of this particular we can say compression member. So after that, before we proceed further, we can have a basic idea of what kind of structural steel members primarily are used in the we can say industrial buildings or any kind of factory buildings. So in majority of the cases we do use the I section, and what we usually do, let us say this is the portal frame, and in this portal frame, let us say we can say this is basically the portal, and this is basically the vertical member that is taking the compression. But at the same time, what we can say is that it is also taking some bending moment also. So that aspect that shall be discussed in the combined actions lecture, where we shall be discussing that how we can study the effect or check the compressive capacity and the bending moment capacity also, and how they do do the interaction. So practically we were discussing about this particular part here first, that when we're talking about the compression members, the primarily aspect is the height or the length of this particular compression member that determines how much compression or how much compression force it can take. So that is the important concept. Second concept that we before we proceed further and study the interaction curves and all, you do need to understand that what exactly is the basic principle of the compression, or we can say determining the compression capacity of a structural steel member. The simple basic equation is that what we can say is that N is equal to AN into Fy. Now, if we are talking about the N, so let us say this is basically the we can say compression capacity. This is the compression capacity that needs to be multiplied with the AN, that is area of the structural steel member. So let us say this is the I section, and whatever area of the structural steel that we are seeing in this particular view, the area of this flange, the area of this web, and the area of this flange again, that shall be the value of the AN. So let us say the area of the we can say this particular member is 1/200 mm square. That can be multiplied with Fy. This is just a random number. So that can be multiplied with Fy. So let us say the grade of the structural steel, that I section that we are using is 250 Newton per mm square. So mm square gets cancelled with the mm square. So what we can say is that 1200 is just simply multiplied with 250 So gives us the value, and that is basically the compression capacity of this particular member in Newton. So 12 to the 24, 300, and again we have this 1, 2, and 3, 0. So we have this in 300 kilo Newton as the compression capacity. Now the important thing that we do need to understand is that if we are dealing with this particular equation, we are assuming that this particular member is very stocky. Stocky means that the section size is very high. Let us say the section size is what we are taking is UB 610. But at the same time, let us suppose the height is only 400 mm. So with this kind of behavior, the member becomes stocky, and simply what we can do is that we can simply multiply the cross-sectional area of the structural steel member, multiply it with the grade of the structural steel, and then simply we can determine the compression capacity. But all this, that rarely happens when we're talking about the practical structural steel design. That is just a, we can say, concept that we first need to understand, that for determining the compression capacity, just simply multiply it with the area of the structural steel member and multiply it with the grade of the structural steel. The same approach we had followed when we were discussing about the design of the tension members. The same principle can be followed here. Now, what happens is that, let us say we have these, two members. We have this one structural steel property member. Let us say it is UB305. Now this UB305, we have to, use it in two cases. In first cases, again, we have this compression member, or we can say column. The height is only, let us suppose, 3 meters. In the second case, let us say the same structural steel members, we have to use it, but the height is approximately 10 meters. So this is also UB305, and this is also UB305. Now the question here is that whether the compression capacity of the same structural steel member property, that shall be same for the height of 3 meter and 10 meters. The answer is no. It shall not be same. Now, why it shall not be same is that because basically here, the Euler capacity action comes. So what will happen is that, when as the height of the structural steel member increases, buckling happens before the member yields. I am repeating this line here. As the height increases, for compression members, what will happen is that the member shall buckle before it yields. Yielding action, this is the formula that we use. But for the buckling action, for buckling, we have to consider the Euler formula to determine the compression capacity considering buckling. So with that, the formula, if you remember the Euler formula, that was basically pi square multiplied with the modulus of elasticity multiplied with what we can say as the area again, divided with the slenderness ratio, that is L by R minimum. Why R minimum? Because we shall be dealing with two kinds of, we can say, radius of gyration. One is the, we can say, major, and one is the minor. One is the, we can say, maximum. The second one is the minimum. So in here, if you will see, what will happen is that this is basically the compression capacity NC. That is basically dependent, the formula of, we can say, L, or the height, that is basically the denominator. So as the height increases, the compression capacity decreases. So that is what we can say the basic equation here. That is, the compression capacity is inversely proportional to the height or the length of the compression member. So that is the important formula that you do need to understand. Now, how AS4100 help us in determining the capacity of the compression members? So the first thing that you do need to understand is that the code is saying or guiding us regarding the concentrically loaded compression members. So that is the term that is used in the AS4100. Why it is, talking like this? Because first of all, you do need to understand that the load is acting at the, we can say, exact center point. Only then we can say the formulas are applicable. Second thing, the formula that is given in the code is basically ns is equal to kf multiplied with an and multiplied with fy, and this is basically the nominal section capacity. This is basically the nominal section capacity. Now again, the nominal member capacity, that is basically the same but multiplied with the alpha c. So alpha c, that also we shall understand that, when we are dealing with the detailed design. So this is basically the nominal section capacity, and when we're talking about the nominal, what we can say, member capacity again, so that is basically nc, and that is basically alpha c multiplied with kf multiplied with an and fi. Now kf here, kf is basically the section form factor. Section form factor. Now, there are these 2 to 3 different principles that needs to be understood before, we start doing the practical design. So we shall discuss in detail about all of these terms. But before that, let me just show you the various codal provisions that are given in the AS4100 code for the compression members. So this is basically the nominal section capacity that we have already discussed a few minutes back. That is basically kf into an into fy, and ns is basically phi into nc. Phi is basically the capacity factor for the compression members. As you know that for the phi for the compression members is zero 0.9. So that is one aspect, that okay, whatever capacity that we are determining, either it is nominal, we can say section capacity, or we can say nominal member capacity. So both of them has to be multiplied with the, we can say, phi, and that is basically 0.9 as per AS4100, and we can say table 3.4. Now after that, the line that is given in the code is that the concentric loaded member subjected to design axial compression shall satisfy both of these equations. One serving the, what we can say, section capacity, and the second one, that is basically the nominal member capacity. So both of these equations need to be satisfied. One aspect is that. Second aspect is that regarding the form factor. Now form factor kf that we have discussed few minutes back, that is basically ae divided with the ag. Ae is the effective area, ag is the gross area. Now the concept for ae and ag is that, let us say this is the very wide built up section or fabricated structural steel section that we are having, and let us say this thickness is only 8 mm and this thickness is again only 6 mm, and this is approximately, let us say, 400 mm, and this is approximately, let us say, 300 mm. Now what will happen is that in the case of the compression force, it is that this cantilever part, that shall not be effective, or we can say that shall not be activated to take the compression load. That is why the code says that we have to use the AE factor, that is the effective area that shall be participating in taking the compression load. That only needs to be considered. So let us say the effective area is only 80% of the gross cross section area. So the KF value comes out as 0.8, and whatever value that we are calculating here, that simply needs to be multiplied with 0.8. So that is the meaning of the KF. AN is basically the net area of the cross section that we have already discussed in detail, and Fy is basically the yield stress of the structural steel member. After that, when we are talking about the nominal member capacity, that is when we're dealing with the NC. Now, you need to understand that NS, one aspect, NS is nominal section capacity. And when we're talking about the nominal section capacity, we are talking about the form factor, that is AE divided by with the AG. But when we are dealing with the nominal member capacity, we are dealing with alpha C factor, and alpha C is basically the member slenderness reduction factor. Now, this approach is very simple and straightforward. How it is straightforward is that, before I explain you the alpha C, let us just discuss this table here. In here, you will see that the modified member slenderness, lambda n. Now, lambda n is nothing but L divided with the what we can say R minimum. So when we are dealing with the lambda, or we can say what we are doing is that we are this dividing the length or the height with the radius of the gyration. Now, as the height increases, your lambda increases. Again, we come back to the same question that let us say it was UB305. One length was approximately 10 meters, other length was 3 meter. So for this particular 10-meter length, your lambda was higher. For this particular value, where the height of the column was only 3 meter, your lambda was lower. So for the high lambda, here we can see that our alpha C factor. This is basically the table for the alpha C. What is the meaning of alpha B? That also we shall be discussing shortly. But just to give you a brief idea, first of all, here, let us say our member lambda n is approximately 25. So whatever value that we are having, alpha C, so sorry, ns, alpha C into nc, just a minute. So whatever value that we are having here, ns, that needs to be multiplied with what we can say as the this particular value. That is, considering alpha b as 0, our value comes out to be 0.96. But again, the same section where let us say the alpha b was 110. Let us say here alpha c is 110, and in here our alpha c is 25. So in here, whatever value that we are having, that needs to be multiplied with 0.961. But in here, the value is 0.477. So the summary is that in here, when we're talking about the capacity difference, the compression member capacity difference, it is approximately, we can say, half of what we are getting here. So as the height increases, the compression capacity decreases. Now, this aspect of alpha B. Okay, so we have understood. Let me just, brief you everything again. We have discussed about the KF, AE divided with the AG, we can say section form factor. And the reason here is that the whole section does not get activated at the time of the compression. AN is the net area of the cross section that we can just simply, refer from the steel tables. Steel table means the one that is, provided by the vendor. So in here, all the, what we can say, this is basically the gross area of the cross section. So if you're talking about 380 PFC, this is the value that we shall be, dealing with or applying it in the calculation. And Fi is basically simply the grade. It can either be 250 or 350 or 450. So that was the aspect of the nominal, we can say, section capacity. But when we're dealing with the nominal member capacity, we have to again multiply it with the alpha C. That again depends on the two factors. One is alpha B and the second one is the lambda. So when we are dealing with what we can say alpha B, now just to give you a brief idea again, if we are referring to the American standards, that is AS41002020, it only gives us the one, we can say, compression member capacity curve. If we're talking about the compression member capacity curves, it looks something like this. On this axis we have this modified slenderness ratio lambda, and on this particular axis we have this value of the alpha C. So in AS4100 we have these 5 different curves of what we can say alpha C. So if we're referring to the American standard, that is ASC360, we only have one curve. But if we're referring to the AS4100, that is Australian standard, we have 5 different curves. So for classification of 5 different curves, we have this value of the alpha B. So on the topmost part, we have this alpha B as -1. And on the bottommost curve, we have this alpha B as +1. Now, alpha B is basically what we can say minus 0.5 for the section. That is hot formed RSS and SHS, cold form RSS and stress relieved and non-stress relieved. If you're talking about alpha B as 0, we have the simple UB and UC sections that are available in the market. Welded H and I sections, we have 0.5, and other section notation table we have this one. Now the simple fact is that, if we are referring to the hot formed RHS and SHS, they offer very, we can say, refined behavior or a very good behavior against the compression loading. At the same time, when we're talking about the welded H and I section, they offer the, what we can say, the least desirable behavior against the compression member. So that is why, as per the code, we have to reduce the capacity. So to reduce the capacity, again, here you can see that if we're talking about the values of the alpha C for different alpha Bs, again, so if our alpha B is -1, alpha C is 0.973. But if your alpha B is +1, your alpha C is 0.818. So the capacity decreases from 0.973 to 0.818. So the capacity simply decreases from here to here. So that is the basic principle of, we can say, application of the value of the alpha C. So these are very, little bit confusing term, but we shall be discussing this and, or doing this in detailed calculations in ETABS. So at that point, they shall be much more clear to you. After that, when we're talking about the lambda n, again, lambda n is basically L by R, L effective divided with the radius of gyration multiplied with the form factor Kf. Now, form factor Kf again is square root of AE divided by AG, and again it is to multiply with square root of Fy by 250. So if Fy increases, then let us say 450 by 250, your lambda n also increases. So that is the, what we can say, basic principle here. So that was the introduction to design of the compression members. There may be some aspect that is not clear to you, but we shall be, discussing in the practical calculations. So this is the practical, or we can say theoretical example, first of all, that we shall be discussing with detailed design calculations. So let us suppose we are having this compression member, although it shall be having the bending moment also, but let us assume in a hypothetical case, it is carrying only compression. So, just as an introduction, these are known as the shear studs. Just draw. Yeah, so these are known as the shear stud. These are basically the steel beams. And on top of that, in majority of the cases, we shall be fixing the deck sheet. And on top of that, we shall be pouring the concrete. So one more thing that you do need to understand is that you can see the one-way action. That is, we can see steel beams only in this particular direction. There are no steel beams in the other directions. So these are the, what we can say, composite beams, which can be designed with Australian standard also and American standards also. So after that, the second aspect that you do need to understand here is that when we're dealing with the theoretical design here, let us assume we are having the compression member here as UC310 into 158. Steel gate, let us assume, is 350 grade. Thickness of the material here is 25 mm. Yield stress automatically decreases because as the thickness is greater than 10 mm, so our Fy is 340 Newton per mm square and tensile strength is 480 Newton per mm square. E is fixed, modulus velocity, that is 2 into 10 to the power 5. That is the value that is fixed. So these are the sectional properties of the structural steel member, that is UC310 into 158. In here we can see section depth, or we can say the root radius, area. This is the term that is important, and radius of gyration. These two terms are the one that are very important to understand. So radius of gyration about x-axis is 139, and radius of gyration about y-axis is only 79. So when we are dealing with the calculation of the lambda, that is L by R. So if R is lesser, your lambda is higher. So that is why I was discussing that we do need to divide with R minimum so that you can get the lambda max, because ultimately it is the same column and it can bend either in this direction, or we can say buckle either in this direction or in this direction. And obviously whichever axis is the weakest, it shall first of all buckle in that particular direction itself. So that is the concept. Let us assume in this hypothetical case we are having a axial compression force of 4000 kilonewton. So let us assume the height or the distance, that is basically 5000 mm. Compression force we know 4000 kilonewton. Net area of the cross section, that is 20130 mm square. That is the property of the structural steel member itself. And after that, the first thing that you do need to understand is that we do need to find out the nominal section capacity. After that, we shall be talking about the nominal member capacity. So if we're talking about the nominal section capacity, we are dealing with the, what we can say, this particular formula, Kf into An into Fy. An we already know, 20130. Fy we already know, 350 Newton per mm square. Kf is the one that is basically 1 here. So that is basically one. How we have calculated Kf, that we shall be discussing with these particular equations. So flange slenderness, what this is the formula that is given in the code to help us find out the flange slenderness, that is Bf, width of the flange minus thickness of the web divided with the 2 times thickness of the web multiplied with square root of Fy by 250. So this value comes out by 6.88. Flange yield slenderness limit is 16. So we are safe here. After that, effective width of the flange, that is given in the clause 6.2.4. So this is the effective width clause that is given here. And in here you can see that the effective width BE for a flat plate element, that can be calculated with the help of this particular formula. That is B multiplied with lambda EY divided by lambda E, and that needs to be less than or equal to B. So that is for the flat plate element, or in our case I section itself. So this is the formula that is being referred in this particular equation itself. That is minimum of lambda EYF by lambda EF, or 1. Or 1 is basically this particular B divided with the B. So lambda EY divided with the lambda E, that is the basic equation. And that again we can say needs to be, what we can say, multiplied with BF minus TW divided by 2 to help us calculate the effective width of the flange, that is 147.7 mm. Now the good thing is that if we are dealing with the, just let me tell you the basic formula here. So in here you can see the 311 minus 15.7 divided with the 2. So here we are having 147.7 number. So here also you can see that the value that is coming is 147.7 mm. So in simple word, what you just calculated, that the whole width of the flange is active against the compression load. Why? Because the thickness is very high, or we can say the member is a little bit on the stocky side. So that is how we can read the results. After that, web slenderness. For web slenderness, that is basically the fixed formula, that is D minus 2 times TF divided with TW. TF is thickness of flange, D is the depth, TW is thickness of web, multiplied with square root of Fy by 250. That is square root of 350 divided with the 250. Whatever value that we are having, that is 20.575. And web yield slenderness limit, that is basically 45. So to check that, we can refer to table 6.2.4. So this is the table 6.2.4. So we can say that this is the hot roll section, and this is again the hot roll section. We shall be dealing with these two values, that is 45 and 16. So if there is one outstand and if there are both outstand. So if you refer to this particular value here, flange. For flange, they have basically taken the one outstand. But for the web, as it is getting supported from both the side. So that is why we are having this as both, and that is why we are considering it as a 45. This is the web, this is the flange. Here this part is free, so that is why it is supported on one side. But web is supported here and supported here, that is why it is supported on both the sides. So lambda EY is basically 45. After that, effective width of the web, again clause 6.2.4, that is minimum of lambda EYW divided by lambda EW, or 1 multiplied with D minus 2TF. So it comes out as 277 mm. Again, the whole section is effective. How? Because 327 minus 25 minus 25. The number comes out to be 277 mm. So here also we are dealing with that particular number only. So effective area of the section, that is 100% of the gross cross-section area, that is 20130 again. So that is how the form factor here is 1, and the nominal section capacity is simply the AN into Fy. And design section capacity in compression is basically phi into ns, that is we are having this value 6159.8. So that is one first stage one. Stage two here is that nominal member capacity in major xx axis and nominal member capacity in minor yy axis. Before we proceed, we do know that when we are dealing with two different we can say values here. So in here you can see that in the minor axis, as I was discussing with you a few minutes back, the capacity is on 4452, but in the major axis the capacity is 5521. So we do need to refer to the minimum number here. As I said, whichever axis is weaker, the column shall simply buckle in that axis itself. And how we have calculated the nominal member capacity, that is again very simple. Effective length for buckling, let us assume it is again 5000 mm. After that, we can calculate the modified compression member slenderness, that is L by R, radius of gyration multiplied with Kf, that is square root of AE by AG multiplied with Fy by 250. The number comes out to be 42.04. This is basically the compression member factor and member section constant. Member section constant for UB and UC, alpha B, that is basically 0. If it would have been RHS or SHS, alpha B would have been 0.5. And if it would have been welded I-shaped section, alpha B would have been minus 0.5. So that is basically the different kinds of values of alpha B, but in our case it is 0 only. So lambda x and alpha x. So yeah, we were discussing about the alpha x. So compression member factor alpha ax is basically 2100 multiplied with lambda nx minus 13.5, again multiplied with this particular equation. So we have two options right now. Either we do know the value of the alpha b, we have calculated the value of the lambda also, that is 42.04. So alpha b in our case is 0 and lambda in our case is 42.04. Now either we can do the manual calculations, which is we can find out all of these coefficients, or we can just simply go to the table here. In this table 6.3.3 section C, here you can see that alpha b in our case is 0. In here modified lambda n, that is basically 40 and 45. So the value shall be, we can say, interpolation between 0.884 and 0.905. So it should be in the range of 0.89. So that is, we are talking about 42. That is also the average of this. So it is approximately 0.89. So we can just refer here, and this is again the value of the alpha C. So alpha C in our case is 0.896. So that is how we can just simply skip all of these detailed calculations, and just we can simply refer to the table 6.3.3c and find out the value of the alpha C. So this is the formula for the alpha C, basically that is given in the code here, that is 1 minus square root of 1 minus 90 by, we can say, these particular symbols here. So either you can do all of these detailed calculations, or you can just simply skip this part and just simply we can say refer to this particular table here, and from this particular table you can just simply find out the values of the alpha C. So as a theoretical understanding, you can just simply for a once do these calculations, but when we're talking about the designing in latest ETAP software or space gas software, so we don't need to spend our man hours on these particular exercises. So that is understood that we can just simply find out this particular value. After that, for in minor y-axis, you can see that when we're dealing with the ry, our slenderness, we can say, compression or lambda increases. In this particular case it was 42, but in this case it becomes 73.87. And alpha b that is again 0 because it too depends on the shape of the structural steel member. So with that, we can just simply, go to this part here again. So in here, we are dealing with this particular values, but it's between 0.748 and 0.715. So it should be in the range of 0.73. So here we can just simply see that our alpha C is 0.723. So multiplying it with this particular, we can say NS. So the number comes out to be 4947, which is again multiplied with the 0.9 to gives us this value, that is 4452.3. So the capacity that we finally need to take is basically 4452.3. So nominal section capacity, that is basically we can say NS, which is again multiplied with the, we can say, alpha C, and that value is again multiplied with the phi, that is capacity reduction factor 0.9, to give us the value of what we can say the nominal member capacity. One more thing that you do need to understand here is that, in this particular formula we are using NS, we are not using NSC. So that is just a value that we are having in comparison here, that is 6159.8. But and that value shall be compared with this, and that value shall obviously be in majority of the cases high only. So this value here, that is 6844.2, that is multiplied with the alpha C value here, and that is again multiplied with the phi here to give us the value of the design member capacity in compression along x-axis or y-axis. So if required, we can have a discussion separately on these particular formulas, but these are just simple formulas that are given in the code itself, and you can just simply enter these values and find out the value of the alpha C. But as I said, in all the country codes, let us say it is American standard, European standard, Indian standard, Australian standard, New Zealand, obviously that is same as AS41 and NZS 3404 1997, that is same. And majority of the cases when we're talking about the behavior of the different types of compression members. So we can just simply refer here and just simply find out the value of the alpha C. So that is the basic, understanding that you do need to have. Now we have discussed in detail about the design of the compression members. We have discussed in detail of what exactly are the theoretical formulae that are given in the code. What is the meaning of the alpha B? Alpha B, as I said, is basically dependent on the shape of the cross section. Alpha C is the factor. Alpha B depends on the shape. Alpha C, that basically we can say depends on the lambda of the section. And we are talking about the two different capacities, that is nominal section capacity NS, and we are talking about the nominal member capacity, that is NCC. And whichsoever is the minimum, that shall be used here to find out that whether the value of the the member that we are using is safe or not. So that is the basic calculation for the compression resistance of the, in our case, UC member.